So I know you thought that all of that terminology in the last video was so fun. You wanted another video talking about terminology. Well, here is this video for you. So we'll start with some easy definitions and then talk about some maybe more interesting definitions. But our first definition is going to be adjacent. Okay, so what do you think it means for two nodes to be adjacent? Well, you probably know this already. All right, so two nodes or vertices, because again, vertices, we can also use the word node. Edges, we can also use the word like relationship. Okay, two nodes are adjacent if they have an edge between them. Yep. So an example of two adjacent nodes are John Wilkes Booth and Ford's Theater. John Wilkes Booth is not adjacent to Abraham Lincoln. I know these two nodes look like they're... Why am I using yellow? I can't read that. I know these two nodes look like they're positioned next to each other, but as we're going to talk about in the future, the position doesn't matter. So this does not mean adjacent. Adjacent means connected with an edge. Okay? It's connected with one edge specifically. So even if there's a path between those two things, that still doesn't count as adjacent. It needs to be one edge connecting these two nodes. And then, speaking of which, what does connected mean? That's what we're going to talk about next. Okay, so two nodes can be connected. And actually, I really don't want to use this word right here. Two nodes, let's say two nodes with one edge between them. Because connected is going to mean something a little different. So two nodes are connected if there's a path between them. Okay, so it's slightly different. We have two similar concepts, but one has an edge between them and one has a path between them. So John Wilkes Booth and Ford's Theater, right, are both adjacent nodes and connected nodes. But Actor and Ford's Theater are not adjacent, although they are connected. Okay, so connected versus adjacent is a subtlety here. So all adjacent nodes are connected, but not all connected nodes are adjacent. Okay, so those are connected nodes, but to make matters even more confusing, we also have connected graphs. So that's a similar definition, but not quite the same. So if a connected node is that there's a path between them, what do you think a connected graph means? Does it... And do you think this is a connected graph? I mentioned this a little earlier. This is not a connected graph. A connected graph means every two nodes, or you could say all nodes, right? Every two nodes are connected. And I noticed, all right, there's too many of these. I need to go back to saying vertex and vertices. I tend to default to saying nodes, vertices, and nodes. We're going to be using those synonymously, okay? Same words. All right, so if you notice me flip-flopping, they mean the same thing. So this is not a connected graph. So let's use some more of these, okay? I'm not going to worry about digraphs too much, right? Well, I'll say it, right? No, I won't. Let's not talk about digraphs just yet. But here, this is a connected graph, right? Every two nodes are connected. Between every two nodes, there is a path that connects them, okay? Now, if we had an island over here, if we had Hawaii and we were talking about driving, then yeah, it would not be a connected graph anymore because Hawaii would not be connected with any of these vertices. All right, so that's the idea for connected. And that's the idea for connected vertices, connected graphs, and adjacent. So next definition is the degree of a node, the degree of a vertex. Okay. What do you think the degree of a vertex means? Well, degree, a lot of times in math, we think of like the degree of a polynomial, right? Maybe of like the intensity, how high of a level it is or something like that. So the degree of a vertex is going to be how many edges it has. So the number of edges for that vertex. So Sonny Liston, right, would have degree 1. George Foreman would have degree 2. And we can even specify this more with a concept of in degree and out degree. Well, what do you think these mean for a digraph? The in degree, right, is going to be the number of edges going into it. So Sonny Liston has an in degree of 1. And out degree will be the degree of edges going out. Okay, so Sonny Liston would have an out degree of 0. Okay, I think that's our only digraph in these examples. We have some more digraphs later. But again, we could look at Fredericksburg over here. What's the degree of Fredericksburg? It's 3, right? There are 3 edges connecting Fredericksburg. All right, in degrees and out degrees don't really make sense here because it's not a digraph. This is an undirected graph. All right, 2 more definitions for this video, and then you can take a breath and release it, because after these 2 definitions, we are done with definitions for a little while. Whew. Okay, so here we go. 2 more definitions. Cycle. Cycle is a path that begins and ends on the same node or vertex. Okay. So again, be very careful. The direction matters here. So we could make lots of cycles for all of these graphs, right? We could have a cycle between Muhammad Ali and Joe Frazier. That'd be a cycle. We could have a cycle from Muhammad Ali to George Foreman to Joe Frazier back to Muhammad Ali. We could not have the cycle going the opposite direction. We could not have a cycle going to Joe Frazier because, George Frazier can't get to George Foreman. Not directly anyway. There's a path between Joe Frazier and George Foreman, but there is not an edge in the right direction between Joe Frazier and George Foreman. Okay? Whereas undirected graphs are a little easier for cycles, right? You don't have to worry about the direction. Here's a cycle over here, starting and ending at Fredericksburg, or starting and ending at really any of these. Okay, so that's the idea of a cycle. The last definition, this is the fun one, okay? Because we have a new graph to play with for this last definition. And the last definition is a directed acyclic graph, abbreviated DAG. All right, so this is a directed acyclic graph. Just a graph that is a digraph and is also acyclic. And yeah, one more thing to mention about cyclic graphs, right? It begins and ends on the same nodes, and it doesn't traverse the same path twice, right? It doesn't go over the same edge. You can think of it as it doesn't reuse edges. Okay, so that is a very important thing as well. So we couldn't have a cycle. There are no cycles that involve Washington, D.C., for example, because anything that would go here would have to come back from Fredericksburg. Now, in reality, yes, there are cycles for Washington, D.C., but not with this graph. So the last thing is a DAG, a directed acyclic graph. We know what directed graphs are. Well, what do you think acyclic means? There are no cycles, right? Probably pretty self-explanatory. So it's a graph with no cycles. So let's look at an example of this. And in general, directed acyclic graphs are often used for things like dependencies. It can be like project workflow. It can be like thinking of college course prerequisites, right? You need Calc 1 to take Calc 2. You need Calc 2 to take Calc 3. Although then it's a little interesting because you don't need Calc 3 to take Calc 4 at this college. But let's not overcomplicate things. Here's an example of a DAG. Let's think about making brownies. And you can thank the author of our textbook for this wonderful DAG right here. So here we have a directed graph, right? It's a digraph. It's got some arrows. And furthermore, it's acyclic. There is no way to make a cycle here, which is great because if you think of the directions to make some brownies, if you think about using some brownie mix to make some brownies, you're following instructions. Maybe you're not very good at cooking. If you ended up in a cycle, you would be having some serious problems here. Okay. Nobody wants to get into an endless cycle of cracking 2 eggs, mixing things, baking it, cracking 2 more eggs, mixing things, baking it. Ooh, we don't want cycles in our DAGs, just like we don't want cycles when we're baking brownies. And furthermore, we do want this to be directed as well. We want some dependencies, and we also don't. Yeah, another way of like loops, right, is if you had a loop, then you would essentially never be able to get started either. Okay, so here we have a lot of things. I think it's pretty self-explanatory for this. You have to do one thing before you can do the other and stuff. All right, so that's pretty much it. The next videos, we talk about some other properties of graphs, like how spatial positioning doesn't matter. We're going to talk about the relations to sets. We've already touched on both of those, so the next 2 should be pretty nice. All right, stay tuned. And yeah, welcome to graphs with all of its lingo and language. Have a good one.